Hello. In this video on derivatives, we are going to review the definition of the graph of a function, and we are going to see examples of some graphs of functions. The requirements are simply to know what the domain and the range of a function are, and a very basic mathematical symbology. We are going to begin with the definition of a function's graph. The graph of a function is defined as the following set. It is the set of pairs of the form x, f of x, where x belongs to the domain of f. Remember that the domain of f is the set where the function is defined. The pairs are as follows. Here we put the value of x, the one we want, and here we put the value which is obtained after having applied the value of x to the function. Let's see an example. Assume that the function that we are going to consider is f of x equals x squared. In other words, the function assigns to each value of x its square. Remember that the domain of this function is the set of all the reals. Does it have its graph? The graph is the set of the pairs of the form x squared, where x belongs to the domain that I have mentioned, which is the set of the reals. How do we represent this? If we take the coordinate axes x and y, then we have the following representation. In horizontal is the x-axis, and here is the axis of y, and each pair is a point on this graph. The first coordinate is represented on the x-axis. The second coordinate represents the y-axis. We have that, for example, if the value of x is equals 1, you know that 1 squared is equal to 1. Therefore, the point you have will be this one here, 1, 1. The value for x equals 2, 2 squared is 4. Therefore, the value for 2 would be 4 that you have here. It is the extreme of this graph. Here we have the graphic representation of a function that is very famous and actually used a lot, which is the parabola. Let's look at a slightly more complicated example. It will also help us to review some important concepts that we see a lot during the first year of the degree here at the Polytechnic University of Valencia. Let's try to represent or simply calculate the graph of the following function. We take the function f defined as the square root of 1 minus x squared, and we are going to restrict ourselves to the domain which is in the interval minus 1 up to 1. We will only represent minus 1 and 1. Which is the graph of this function? In reality, it would be the pairs of the form x, square root of 1 minus x squared. For each value of x, you have to calculate the square root of 1 minus x to the square and represent the coordinate axis. Now, what shape does this graph have? How many points do we need to represent it? You could make a small table with several values and give value to the value of x, for example. 1, 0, 1, minus 1, and more or less sense how would be the graphic representation of this function. Let's attempt to clarify what it would look like using a formula or equation that is indeed crucial. Look at the following. To begin with, considering this notation, y equals the square root of 1 minus x squared, we will always denote by the root of a or any value the non-negative square root. That means that if this is going to be always non-negative, the variable y, or what we represent on the y-axis, is always positive. Explanation: whatever we represent will be above the x-axis at the top. Let's manipulate a little bit with the equality that we have here. Let's start with the equality y equals square root of 1 minus x squared. If we want to remove this square root, what we can do is square both members of the equality. Doing this, we would obtain that y squared equals square root of 1 minus x squared, all squared. The square and the square root will simplify. Actually, allow me to make a small note here. Would they go? Whenever we put here the module of 1 minus x squared. But note the following. The domain of the function is between minus 1 and 1. All the values that I can insert here are between minus 1 and 1. And do you know what happens when we square a number between minus 1 and 1? It becomes smaller, or it would remain the same in the case of minus 1 and 1. But any number that is within minus 1 and 1, when we square it, curiously, it becomes smaller, it does not get bigger. Conclusion: 1 minus that value will always be positive, and therefore, there is no need to put the absolute value here. Let's continue with the process. We were saying that we are going to square both parts of the equality. The square eliminates the square root. So I am left with the following expression. Y squared equals 1 minus x squared. This minus x squared that is subtracting this part of the equality, we are going to move it to the other part by adding, which is what we just did here. X squared plus y squared equals 1. What is this actually? What does this represent? there is something important you should know, and it is the following. We have expressed the solutions of the equation in a general form, using A, B, and C. We are given points located on a circle with centers at A and B, as shown here. These points, A and B, serve as the center of the circle. And this value, the square root of what we have here, represents the radius C. All right? If we consider the center of the circle as the coordinates 0, 0. That is, if we set both values here to 0, we would have a circle centered at the origin, at 0, 0, as you can see here. And if we take the radius C equals 1, then the equation that we obtain by subtracting the A, B, and C by the values that we have taken is this here. X squared plus the square root is equal to 1. And this is its graphical representation. Sorry for the representation because it looks more like an ellipse than a circumference. But actually, this is a circumference with center 0, 0, and radius 1. This equation here, in reality, is a circumference of center 0, 0, and radius 1. It is very important that you remember this formula because it is applied a lot of times. In this case, it would be very easy to identify that the center is the 0, 0, and that the radius is 1. But I would like that if in the end it would appear some other equation in which the center would not be 0, 0, you would recognize it immediately. Doesn't this ring a bell? If we look back, this is the identical equation we previously had. We are going to put together the things we know. Look, this equation defines two functions. Allow me to explain this note for a moment. If we solve for y in this equation, we have the following. Let's do a bit of the opposite of what we have done so far. The x squared that is adding on this side, I put it on the other part subtracting. Next, I apply square roots to both members of the equality. Of course, when we are solving for the y squared, a plus minus is always added to the square root of 1 minus x squared, because both the positive and negative solutions are valid. Any number squared, whether negative or not, will always be positive. Therefore, this part would always work. Remember to include both the plus and minus square root when solving for something squared equal to any value. The important thing is that I have two functions, the positive root and the negative root. What is the graphic representation of each of these functions? Look, if I take the positive root, what I get is the positive semicircle. And if I represent the function with the minus in front, the minus square root of 1 minus x squared, it is the negative part of the circumference. Both together give me the complete circumference. Let's recap. We were asked from the beginning that given the domain that is equal to the interval minus 1, 1, and the function square root of 1 minus x squared to represent its graphic. I would like you to more or less get the idea of what we are going to do now. Let's see. If this was the equivalent of the function x squared plus the square root of 1, although we put two functions in that case, in this case it would simply be the positive root of 1 minus x squared, which is the superior part of the circumference. Simply that, just this part here. Remember that we have deduced that it was always positive, that this function was always positive. Therefore, we cannot draw the negative part, as it would not make sense to do so. A very important note. This function represents the superior semicircle. It is very important that you remember it because it appears a lot of times. A note. When a function is defined through a formula, as we have done a while ago, it will be understood that unless otherwise stated, if there is no note in the exercise, if no one writes it down that this is not the case, we will assume that its domain and range are subsets of the real number line. That is, we will always take real values and that the domain consists of those real numbers for which the formula makes sense. What does this mean? Let's see. Imagine that we provide the function 1 divided by x and we ask ourselves, what is the domain? You do not have any additional information. Nobody is telling you what the domain of the function has to be. You have to assume that they are all the real numbers, what this paragraph stated. All the real ones, we take all the values of the real numbers in which they make sense. In which they make sense. Notice that the 0 cannot be. This function is not defined at 0. They are all real numbers except the 0. Here is a notational error. It would be necessary to put the 0 between curly brackets because we are talking about sets. The domain, all real numbers except the 0. And the range, In this case, we should draw or represent the function. The function 1 divided by x has this graphic representation. The range in this case would be all the values of y that have the image. This would go from negative infinity to 0, without including the 0, because remember that the 0 is not a point of the domain, and from 0 to positive infinity. All those points are part of the range of this function. Only 0, I insist, is out of the domain, therefore, here we do not have any value. I hope that all of this has been useful. In this video, we have reviewed the concept of graph of a function, and we have seen examples of graphic functions. Thank you for your attention.